So thank you to the organizers for giving me this talk, and thank you also especially for putting this talk at the very end, because after this whole week of extremely detailed talks about every single aspect of SUSY, what I would like to do as we end is sort of give you all a bird's eye view and a phenomenologist's perspective of where we are after run 2, basically. So let's start from the very beginning. I mean, obviously nobody here needs to be explained this, but there are some students, so just to have an overview of everything. So we have these different sectors in the minimal supersymmetric standard model. And generally there's a strongly charged sector which contains a gluino and some quarks. There's an electrically charged sector which contains Gauginos, the charged leptons, and one charged Higgs, and these can generally be produced directly via HL-LHC. So the reason of dividing these into sectors is just to sort of categorize what kind of production mechanisms we have for them. Then you have electrically neutral fermions, so you have the neutralinos. So usually you produce them in cascade decays, not directly. And you also have electrically neutral scalars, neutrinos, and some Higgses. And again, these are kind of hard to produce at the LHC directly. Because the LHC is a PP machine, so you would normally produce them in the cascades of some other heavy particle that you produce. So this is generally how we go about it. And this determines what kind of searches you have for SUSY at the LHC. And currently, both ATLAS and CMS use the trick of using simplified models, which simply means you choose the main particle that you want to produce, and you choose only one decay mode of the particle at a time. This is, as you can understand, quite simplifying and allows you to cover all different kinds of possibilities of decay modes. However, if you actually try to generate a realistic SUSY benchmark, a realistic SUSY model, you hardly ever have 100% branching ratio into only one channel. Usually most new particles have multiple decay channels that are open to them. And therefore it is not always trivial to map the results that have been shown here using simplified models to realistic SUSY scenarios. So that is one of the challenges that a phenomenologist has, which is to understand how these searches translate to what it means for your physics requirements. So these are the searches that you normally do. Is first, if you're producing strongly charged particles, then you look for them in jets plus missing ET, or some leptons plus jets plus missing ET. If you're trying to look for electroweak charged particles, then you have some leptons plus missing ET and maybe some jets. And of course, now we have expanded our searches to also look at either super compressed or some regions of parameter spaces where the new particles that you produce might actually be stable on the detector scales. So these are what are called long-lived particles. And if you have long-lived particles that are electroweak charged, then you would normally have some sort of tracks because it's electrically charged, so it will give you a track signature. If it is a strongly charged long-lived particle, then it decays in a normal way into some jets and so on. But since the decay is going to be away from the collision point, you have what are called displaced vertices. So this whole program sort of covers all possibilities that can happen. And all the new searches that are coming out are really not as simple as just enumerating the number of particles that you have, but make use of extremely complicated signal regions, multiple cuts, and often also either boosted descendant trees or neural nets or heavy machine learning machinery. So the challenge then is to understand what these searches mean for us when it comes to understanding the physics and the motivation for why we want to have a supersymmetric model in the first place. So most of our interests sort of can be distilled into these three questions, which are of interest to most phenomenologists. So the first question, so these are the three questions that I plan to address in this talk. So the first one is relates to dark matter. So we've heard that supersymmetry gives us a natural dark matter candidate. And so the first question that I want to ask is, what is the lowest configuration, lowest mass configuration that is compatible with all the LHC searches that we've had so far and the direct detection constraints that we have. So we had a very detailed discussion about this by Geneviève Belanger a couple of days ago. So of course, take a look for all the caveats. I'm going to give an overall answer. The next question is about also related to the dark matter question, where we have this idea of Stau co-annihilation, which gives the right dark matter density. And so what is the status of that particular scenario? And finally, since the motivation for LHC scale supersymmetry has for a long time been this idea of naturalness, and the lowest strongly charged SUSY particle is the stop, we can ask what is the lowest stop mass that is still allowed. And this was also commented on by Manoranjan at the beginning of this conference. So I'll just give some more. And of course, we've had a whole talk about stop and bottom searches just before this. So I'll just give a very short answer of what we get from using some codes that we have. Okay, so to understand, since we are going to try and answer the question, how low can you go? What is the lowest possibility? So we have to ask the question, how do you escape a SUSY search? And of course, there are model building answers to this, and a huge list of those model building answers was discussed by Vishwarup again in the beginning of this conference. But what I'm going to talk about is sort of the bottom-up approach, which is these are the searches that we have, and if you want to escape detection in those, what do you have to do? So the first is quite obvious. You just have particles that are so massive that the production cross-section is very low. So that's the obvious way of escaping a search. The second method, again, by now, well known to almost everybody, is the idea of compression, where you have, since supersymmetry works in a way that you have cascade decay, so you produce one particle and at the end you have this lightest supersymmetric particle, which is normally neutral and stable. If you have a very compressed spectrum, which means that the masses of these two are very close together, then the products that are in the cascade in the middle, even though you have them, they might be too soft to detect, and therefore you may escape the search. However, another thing that we should note is that since the LHC is a PP machine, you have lots of initial state radiation. So just a thing to remember when talking about compression is just taking tree level calculations may not, or rather I should just say taking leading order calculations are not enough. You need to take into account initial state radiation jets, ISR jets, and that sort of still gives you some limits. So it's not that if you put the compression to zero, that you get nothing anymore because you can't detect anything, but because you have this initial state radiation, you get still some sensitivity in your searches. The third possibility is that the particles that you produce have a long lifetime. So the products that we usually trigger on and put cuts on are not attributed to the primary interaction vortex, or they just look very strange. They look like pileup, they look like coming from somewhere else, and so we might throw them away. And finally, one thing that is not normally addressed as often when talking about these simplified model searches is that if you have a large number of branching fraction of decay modes that are open at the same time, then you might have a different problem where none of the decay channels are sensitive enough, or rather have enough number of events that you might make a discovery, but all of them have very small number of events here and there, and you finally miss the model. So that is also a possibility. So these are all things that we should keep in mind while asking how low can you go. Okay, so I'm not going to go to the details of these summary plots, but I just want to flash them to give you an idea of what's out there. So let's start with the strong searches. So for strongly charged particles, the most popular particle is the gluino. So the gluino can, if it's heavy enough, it decays via QQ bar to and then a lightest neutralino. So you can write all possible kinds of decay channels, and you can see you have a limit on the mass side of about 2.2 TeV. And then, of course, as you go to the compressed side, you see still at the lower edge, the line is very smooth. So basically, as long as the decay is allowed kinematically at all, you're ruling out that particular point, which simply tells you that the cross-section is so large with ISR that ISR gives you enough missing energy or whatever it is you need to pass the triggers and to have sensitivity in these searches. Okay. So these nice straight lines mean something. Then we can go to squarks and stops, and we had a very detailed talk about stops just now. So again, you have limits of the order of say 1.3 and 1.3 TeV for the stop and 1.8 TeV for the squarks. And as you can see for the stop case here, you have the overlapping limit is a combination of 0, 1, and 2 lepton searches. So it's not just one search that is fully sensitive, but if you combine all possibilities, then you get this envelope that's large. So this is something that, of course, the experiments can themselves do, but it's kind of hard for phenomenologists to replicate because we don't have yet a sensible way of combining different searches. So that is something that needs to be done. Okay, so that was the strong sector. Then we come to the Gauginos, and the plots are quite similar. You have the particle that you produce, the mass of it on the x-axis, and the mass of the lightest guy on the y-axis. And you can see here that the limit lines sort of seem to deviate from the lines of maximum kinematic allowed limits. So this is telling you that the effects of compression are starting to make an appearance here. And you can see that the upper edges in some cases are getting to about 1 TeV. And this 1 TeV number is sort of significant because of dark matter concentration. So that is why I'm just attracting your attention to that number. However, you should still remember that when the limit is about 1.3 TeV, the mass difference is still 500 GeV. So it's not like 1.3 TeV of Gaugino also implies 1.3 TeV of the lightest neutrino. That is not detectable as of yet. So that's one thing to remember, that the compression effects are very strong here in this sector. And secondly, often we get used to seeing data presented in this format without always keeping in, we just get used to having these kinds of mass relations as an assumption, which may not necessarily be true in the case of a purely phenomenological SUSY body. So these are, of course, motivated by some very well-motivated physics considerations, but still you might have situations where this is not exactly true. Okay. Okay. So let me also just remind you of the, so we've been talking about these simplified models and looking at plots in this simplified model picture. So let me just remind you also of the known pitfalls of relying on the simplified models. So first of all, in all of these cases, these ones are particularly easy to see. You can see that 100% branching ratio only into one particular final state was assumed, right? So often, since in our parity conserving SUSY, always we produce 2 SUSY particles at a time. If you have an asymmetric decay case, so one of the particles decays in one way and another decays in another way, then simplified models will miss this topology. So because they always only assume one branching fraction at a time. So that's an obvious drawback, and codes that rely on interpretations using simplified models sort of generate then these missing mixed topologies to fill their parameter space. Secondly, if you are designing experimental signal regions and then rely only on these simplified model topologies, then there is a danger that you might miss some optimization because you are sort of biasing yourself to only look at that particular channel. Next is about dilution. So I already mentioned this a bit more, but another thing that happens is that when you have these searches, you have a sort of blind analysis, right? So you choose what signal region to use to exclude your model before you actually look at the data. So you do some expected signal strength analysis, and based on that, you already choose what your best signal region is going to be. So which means if you have 4 different branching or decay modes open at a time of approximately equal strength, then basically you are only sensitive, and the symmetric chain idea means that both of them have to go into the same decay mode, which means you sort of have this 1/16 factor of reducing your sensitivity. So to get rid of this last point, what we need is a way to combine different signal regions. And of course, for this, it's not the topic of this talk, but it's a discussion that has been happening on a larger scale. And you can, in this conference as well, we've had talks by Harrison, by Wolfgang, and also the experimental discussion, I'm sorry, I forget the first name, by C. Campagnari for these issues. However, I'm criticizing simplified models a lot, but there are 2 things that we should remember. First of all, they are very simple, which is actually of great value. And secondly, using simplified models makes sure that all signatures are covered, whether or not they are the dominant ones. So sometimes you might have a decay mode that happens only 0.1 or just 10% or even 1% of times, and you would normally just ignore it if you go to look at real phenomenological models, but maybe nature is something different than what we expect. And so having this simplified models has the advantage that you're looking at everything without biasing yourself beforehand. So that is the advantage of having simplified models. Okay, so now you have all these simplified model limits, and how do they compare to realistic SUSY models? So this was a question that was answered a few years ago in this paper by ATLAS. So ATLAS took their own searches and did a scan in the PMSSM, which has 19 free parameters, and tried to just say how many of these models are ruled out, how many are still allowed. So these are the kinds of plots that they came up with, where they basically just give you a fraction of models that has been ruled out by one or more searches, and comparing that with essentially the simplified model exclusion lines that were shown in the previous plot. So these are very useful to see because it tells you how likely a particular how likely a particular search is to rule out all SUSY in some sense. However, I find that these kinds of plots are kind of hard for the brain to digest because it doesn't give you a lot of information about what exactly was happening here. Why were only so many models ruled out, and why not others? So, so to answer that question, to understand what exactly is happening, what you need to do is to be able to test your own SUSY model, or any other model for that matter, using the same analysis that the experimentalist is using, right? And if you are not an experimentalist, then this is kind of difficult to do. So what are your options? The first one is to convince an experimentalist to take your event files. So you do the Monte Carlo job, they take your event files and run them through your analysis and give you the answer at the end, whether your model is ruled out or not. So this is the approach that has been taken by these recast people who are trying to preserve the analysis that can then be used by other people to rerun on other models. The other option is to have this library of efficiencies of all simplified models, all simplified model topologies, and then you can use the upper limits in each of these topologies, reweight them according to whatever the branching fractions are, and then get your answer that way. So that is the approach that is used by models or people who use the simplified model topologies. And the third approach is to sort of re-implement the analysis yourself in a simplified way with some smearing for detector effects, and then you can parameterize how wrong you are. I mean, how well these detector smearing things, how well they agree with what the experiment is actually doing, and so on. And then you have this sort of skeleton which can be used by whoever wants to basically rerun their own model through. So this is the approach of Checkmate, and there are a few other codes also on the market that use a similar philosophy. And the advantage of this is that it relies only on kinematical cuts and so on, so it is as model independent as it is possible to be. So how would you go about doing this? So there are some things that you need to be able to do this. So first of all results that you get from the experiment should be in this model independent, in a model, should be presented in a model independent way. So you give a cut flow of all the cuts for some benchmark so you can validate it. And then you have upper limits on what cross sections are expected to survive these cuts. So this, if you use this, then this is called reinterpretation or recasting. And then there are several, to make this work, as you can imagine, there's a lot of back and forth information exchange that is needed. So there are working groups between theorists and experimentalists that are working on doing this constantly. So one of the main groups that does this is called the Reinterpretation Forum. And last year, we came up with this large list of recommendations of what is missing and what is needed to really preserve all the information in analysis and be reusable. And of course, now with the ascendance of these long-lived particles, we also have a long-lived particles working group that takes care of special issues that come with long-lived particles, because those are not standards, the searches are not standard. So you need a lot more back and forth talk to understand how to reinterpret these searches. Okay, so this is a flowchart of how you would go, or how a theorist would go about implementing and understanding these searches. So you start, so there's the Monte Carlo bit, which is pretty much the same for everybody. You write down the Lagrangian parameters, figure out how you're going to produce the particles that you want with all the physics effects that you want. Then you pass this to your detector simulator. So you simulate detector effects, and using the objects that are reconstructed using this toy detector or whatever, you apply all the analysis cuts, do all your statistical analysis, and then you compare with either published shapes or upper limits or whatever information it is that you have. So this is the general workflow of how this works. And this is a picture of the internals of Checkmate. This is a code that I work on. How Checkmate does this. So there are multiple possibilities. So you can write down the Lagrangian using essentially you want to give it a MATRAF model. You can generate signal events using MATRAF or Pythia. Pythia also does showering for you. Then we use Delphis for detector effects. And you can sort of also come in at each of these intermediate levels. So you can just give a different format files or HepMC file or whatever. Yeah, so you have multiple options of doing this. And then you have these analyses that are implemented. And then finally, what Checkmate gives you as output is the ratio of the cross-section that Checkmate calculates after the cuts to the published upper limit. So that is what you get as an output. Okay. And the current state of Checkmate is that we have 45 total 13 TeV analysis in there now. So that's the largest number among the public codes. And we also have these 5 long-lived particle searches, which can now be used by the public, essentially. So this is our current state. So I won't talk too much about that. So let's go to the questions that this talk wanted to answer. So the first question that we wanted to answer was, what is the lowest Gaugino mass configuration that is compatible with both direct detection and the LHC and gives the right relic density? Okay, so to understand the parameter space that we're talking about, I just wanted to show this slightly old work just to describe the space that we're talking about. So remember, for the Gaugino sector, you have three parameters that are of importance. You have the mass parameters for the Bino and the Wino and the Higgsino, right? And in this 3D space, if you plot the surface of all the points, that can give you the right relic density by whatever method possible. So this does not include freeze-in or any of the very new methods, but the normal freeze-out, including co-annihilation and so on. So you get this sort of surface, and this surface includes the pure Wino region, where you have only Wino component and no Bino or Higgsino, and also pure Higgsino regions where you have only the Higgsino and no Bino or Wino, so on, right? And so the 1.1 TeV thing that I was drawing your attention to is essentially the mass of the pure Higgsino. Okay, so that's the limit of what the pure Higgsino can do. For the pure Bino, the limit is about 2.7 TeV, so it's kind of outside the reach of the LHC, so we can't really get there. The other thing to note here is what is the mass splitting between what you're going to sort of produce, usually, which is the next to lightest supersymmetric particle, lightest charged supersymmetric particle, and the lightest one. So that's the compression. And so these are the two figures for the neutral and the charged cases, right? And you can see that for LHC reach, so this gives you the mass, and the mass that is within our reach is about below what is yellow. So everything that is red or orange, okay, that's what is within our reach. And in that region, you can see that so up here, the splitting is about 10, definitely less than 40 G. Okay, so that is the kind of splitting you expect if you want to get the right dark matter relic density. So similarly, for the charge case, you see that the splitting is 20 GeV or less. Okay, so that is the ballpark number that you need to keep in mind. So that was the point of showing those figures. So this is another way of looking at the same thing. So we looked at, for example, the electroweakino search. We reinterpreted that and tried to figure out what is the highest, what is the best exclusion that you have. So what we find is, so the MCC is for charge genomass, and this is the mass difference on this axis. And we find that the most that you can do, so this was with 36 femtobar inverse, but even including the full data, we see that this and this plot don't have a lot of difference. So I don't expect this will be modified too drastically. It might be modified a little, but let's go with this point for now. So this point is somewhere around 220, and this dotted line that you see is the line where you get the right relic density. Okay, so that's what it looks like. So this is the point that we have to keep in mind, and so that's the answer of the first question. The first question is, what is the lowest mass that is allowed? So this is approximately 200 GeV. Okay. Another thing that we sort of asked in the light of new methods of calculating the dark matter relic density is at what point this co-annihilation and co-scattering transition takes place. So this was in a EFT picture where you can imagine that the Higgsinos are integrated out, but the overall answer still remains relevant for us. And we found that when this happens, essentially, you can think of it as when the mixing or the Wino component of this of the lightest of the LSP is about 10 to the minus 5. And when that happens, if you calculate what the lifetime of your charged partner of the Chargino is, then the lifetime is quite long. So it gives you a long-lived Chargino. So that gives you essentially another motivation for looking at these long-lived searches that I will talk about in a minute. Okay, so then we can, essentially, so the question, so okay, to summarize here, we have a limit of about 220 GeV for the Chargino from that is compatible with relic density and LHC. And if you go to the case where you have very low mixing, you can have the case that it is long-lived. Okay. So then we come to the question of tau co-annihilation. So again, just to cast it in a more simple language. So the idea is that you have a term in the Lagrangian that looks something like this. So you have a tau that couples to some dark matter and the tau. And if you calculate the decay of the tau, what is allowed, if you go to the extremely compressed region, then you reach a point where the two-body decay into the tau is no longer allowed and the tau becomes long-lived. Okay? So once it becomes long-lived, again, you can make use of the long-lived track searches to have limits from there. Okay, so this is the lifetime frontier for the tau. So when I say M5, 5 here actually refers to the tau mass, and on this axis we have the lifetime of the tau. And we have two different searches that have been implemented here. One is the CMS displaced lepton search, where the original search is like this, where you have produced stops and then they decay via some R parity violating couplings into the following way. So you have two leptons and two jets coming out of them. And secondly, we have this ATLAS search for heavy charged particles, heavy charged tracks. So basically you just have a track that goes all the way outside the detector. Okay. So we see that it covers a very large range of lifetime. So all the way from, so this is essentially the decay length rather than just the lifetime. So it goes from all the way from 0.1 millimeter to 10 meters. And there is a gap in the middle, which in principle could be filled by these disappearing track searches, where you have a track that travels a bit and then disappears because you can no longer see the decay products. However, in the case of taus or in the case of any scalars that are electrically charged, the main thing that you need is an ISR jet to trigger on, and having this very hard jet means that your cross section is too low. So we find that actually, even though in principle you should be sensitive, the cross sections are not high enough to get anything. So you have this big gap in the middle.
Nishita, would it be possible to wrap it up in 3-4 minutes?
Yes. I'll be done in a minute. Well, not in a minute, but yeah, in 3 minutes. Yeah. So just to summarize, so I talked a bit about the long-lived part, but we can also talk about the normal prompt decay. And there what we see is actually quite obvious already in the plots. So this is the analysis that we have in Checkmate, the ATLAS tau search. And for both the left and right handed cases, we see that even a little bit of compression, so even a compression of 100 GeV, which is already quite large to be honest, renders the search pretty insensitive. So it's only sensitive when you have very hard objects coming out at the end. Right? So that gives us essentially a sort of loophole of fitting where we want to live. Okay. So then we can go to the last question, which is what is the lowest stop mass allowed. So again, I won't go into great details about this because we just had a long talk about stops. But I'll give you an overview of what we find. So the easiest stop case is where it goes to a top and a neutralino, and there the main way in which you can reduce your sensitivity is by making it more and more compressed. And with large compression, we still find that with ISR you can probe about 500 GeV. You can have so your lightest stop is usually assumed to be right-handed. It doesn't always have to be. You can have other compositions and then therefore other decay modes. So we tried that as well. So you still get a sensitivity of the order of 400 GeV. And you can have this case where you have taus that are also light. So you have this decay mode where it decays not via the top, but via this kind of a decay mode where you have bottoms and taus in the final state. And currently, the newest release of this bottom tau state from ATLAS was just a few months ago, so it's not in Checkmate yet. So our current best sensitivity is actually from Jets plus Med Surge, and again using ISR, you get a limit of about 400 GeV. So that's what we find. So we have a new version of Checkmate that's coming out, which has an update of more full run-to searches, especially stop searches. And the other thing that we're trying to do is to use simplified likelihoods to sort of take care of the problem of having multiple decay modes where you might have your signal distributed in. And finally, of course, there are some code-related things that need to be cleaned up that will be done in version 3 as well. Okay, so this is basically my summary. So these are answers to the questions that I asked. So yeah, so I'll just stop here.
Thank you. Thank you, Nishita. So any questions? Can you please raise your hands?
Hey Nishita, this is Pradipta. Can you hear me?
I can't hear you, Pradipta.
Can you speak up a little bit closer?
Can you hear me now?
Yes, I can barely hear you, but I can hear you.
So just let me just adjust this thing.
I think we can just about hear that Pradipta is saying something, but nothing else.
Yes, he's gone again. Huh?
Yeah, me. So now is it better? Or
Yes, it is a bit better, yes.
Yeah, so I'm trying to be as close as possible. Yeah, so two quick questions. So you mentioned initially about this compass spectra and this long-lived particles. So is it possible to connect them like if there is a super-compressed spectra? Is there a possibility for a super-compressed spectra kind of situation to get soft particle as well as displaced object?
Yes, of course. That's definitely possible. So one of the projects actually what we did was so if you look at these the Chargino going to neutralino and then something else. So if this something the W and you have both compression and this long-livedness, then the leptons that come out from the W are going to be very soft. So in this case, you have displaced leptons that are soft. So that we found out actually that this was a gap in the search because the lepton triggers that are used for the search require the leptons to be at least 40 GeV. That was so then. So we had some work where we sort of recommended what kind of triggers we can.
Yes. No, but what I'm asking, Nishita, that because it is also displaced, so I mean, do you believe that there will be some kind of advantage like compared to the non-displaced object, which is
Pradipta, we cannot hear you.
So he's asking, is there an advantage to having both displaced? So I think what he's trying to get, correct me if I'm wrong, is that
yeah, now it is clear. Now my voice.
no, okay, yeah, we hear you. I think you were asking, is there an advantage that from going displaced because the displaced searches have very low background?
Exactly. That is the question.
Compression you might sort of make up by being displaced. Is that what you were asking?
Yeah, that is true.
Yeah, so that is sort of possible, but I think the problem here is essentially what do you trigger on? So if you have soft and unusual objects, then that is the main question that you have to answer. Either you have hard unusual objects or soft usual objects, and then we know how to do that.
Okay. So, and one quick question. So about this 400 GeV stops, as you just mentioned. So then which kind of AT and the other stop mass that you need to satisfy the Higgs data?
Yeah, so for this actually I must admit that I did not actually worry about the Higgs at all. You're right. You need a very high mixing parameter in the stop sector to get the right Higgs mass.
Okay.
But I have to admit that I was not worried about that. I was just trying to.
No, that's fine. I mean, I was just curious because it's really low.
Okay, Rohini.
Thank you, Nishita.
Rohini, please.
Okay. Thanks. Nishita, I had one query for you. Is that what you have done is that when you say right relic, you actually want to get the actual relic that has been observed, right? I mean,
Yes.
If you had relaxed the possibility that, some other, that this only provides part of the relic, then your neutralino can actually be lighter.
Yeah, absolutely. I mean, so
so in some sense, I mean, the most pragmatic thing would be to demand that it doesn't overclose. That's all I would say.
Okay, yeah, I agree. And to be honest, since the way we do these searches, it means that you're not throwing away things anyway, right?
Yeah.
It is just to answer this phenomenological question about.
Yeah, but
This,
even this phenomenological question, if I remove the boundary condition,
sure.
that I mean, in some sense, I would say, I don't know. I mean, in some sense, I would say, we can provide different answers by asking 3 different questions. One, if it produces exactly the right relic, if it's underabundant, and then somebody else comes and gives me additional dark matter candidate, because we know so little about dark matter. And the third would be even to take even more agnostic, that let it overclose the universe. Some cosmology and early moduli decaying things will make life simpler for me. Can I just find out, what might be the smallest neutralino, just from sort of kinematics and the corresponding couplings? In that case, the direct search limits can be very different, even for a light neutralino charginome, if you take either underabundant or overabundant regions.
Right. So I don't have that plot.
In the spirit in which you are taking first only the kinematics and then evolving downwards, this might be an approach to take, is all I'm saying.
So I only could show a part of what we did. So we did actually take into account the direct detection limits, and we only considered those points that have satisfied those. Anyway, it's not important right now. But to answer your very first question, the answer to that is, if you don't have any other requirement, then you can choose for it. So you don't have to be on this line. So you can be, for example, at 170.
So what I'm saying is that it makes sense to give the how low we can be, but in all the 3 different scenarios. That's all I'm saying.
Sure.
And I didn't mean direct detection. I meant direct detection we have to implement anyway. What we have not seen, we have not seen, no matter what. But what I meant was direct production of electroweakinos. What I meant is that in the underabundant and overabundant scenarios, the rates for direct production can be very different. And therefore, the LHC phenomenology is quite different. And when you are doing this, it might be interesting to show all the 3 in sort of an agnostic manner. That's all.
Sure, point will take.
Thank you. Thanks, Rohini. John, I think you have raised hand, please.
Yeah, thank you. Thank you, Nishita, for a very nice, comprehensive talk. For a reason that you can imagine, I'm interested in relatively light muons. And I wondered whether you've implemented muon searches in Checkmate, and if so, what conclusions you have.
Yeah, so I did not run them specifically for muons, but there are essentially just normal slept-on searches that have been implemented. So we can definitely use one of those. So I can get back to you about what our current limits are. And of course, if you're talking about the long-lived case, then the Stow limits would apply pretty much almost exactly, because it looks the same if it's long-lived.
Yeah, well, relatively long-lived might be interesting, but I wasn't necessarily thinking about them. And I just like to say that if you are thinking about muon constraints, I think it's important to distinguish between the constraints on left and right-handed muons, because the production cross-sections tend to be very different, and so the sensitivities are different also.
Yes. Yeah, I admit that we haven't checked this yet, but yeah, it should be fairly easy to check, so I can get back to you on that. Okay, thank you.
Okay, thank you. I see no hands raised, so let's thank all the speakers, Frank Hetman, Soham Bhattacharya, and Nishita Desai again. So we'll come back for the closing session with the 2 outlook talks, one by Philip Mutkar on the experimental side and the John Ellis from the theory side. So let's, right now this current session is closed, so we'll meet at 5. Thank you. Thank you.